So I'm going to talk about learning to remove Pileup at the LHC with jet images. This is based on work done with Patrick Comiskey, Ben Nachman, and Matt Schwartz. So outline, first I'm going to sort of do a brief discussion about Pileup, the problem, and do some fear-mongering. Then we're going to talk about jet images, which we sort of discussed already, so we'll just sort of lightly touch on them. And then I'm going to introduce our Pileup mitigation from machine learning framework, or PUML. And then I'm going to talk about performance and robustness of the method. And I'm going to try and give you a sense of what the model is learning, sort of crack open a simplified case and get a sense of what's going on. So here is what can be expected at the high luminosity LHC. It's an event with 200 Pileup vertices, and you're looking for the blue needle in the purple haystack. A little bit more numerically, right now, there are about 20 to 40 Pileup vertices per bunch crossing. For run 3, you can expect around 80, and as we just saw at the high luminosity LHC, you can expect around 200. So this is sort of a problem that's really kicking into gear if there aren't good solutions on the table. So is this a problem suitable for machine learning? Well, then there's the question of how to input the information. You want to use low-level inputs, so calorimeter cells in the case of jet images, or particle-level information. What information do we have? For the charged particles, you have a sense of whether or not they come from a Pileup vertex or the interaction of interest, the leading vertex. And then what sort of machine learning architecture should you use? I'm going to make the case that you can use tools of modern machine learning, like convolutional nets, for example, without having to go deep. I mean, you don't need tens of thousands, hundreds of thousands, millions of parameters. And then sort of what loss function do you use when you're predicting jet images? So sort of getting a sense of what other people have done, the way they've used information. There's Pileup for particle identification, or PUPI, where for each neutral particle, which is the information you want to correct, because the charged information, you know whether or not it comes from a leading vertex or a Pileup particle, whereas what you want to do for the neutral information, where you don't know, you want to come up with a way of rescaling or correcting that to just the leading vertex neutral information. So what PUPI does is it looks in an annulus around each neutral pixel or particle, and it uses the ratio and information about the charged leading vertex and charged Pileup information to do a correction. SoftKiller does a sort of interesting dynamic transverse PT cut, and jet cleansing, which is specifically for jets, reclusters a jet into subjets, and then depending on how much of the jet charge information is Pileup, it rescales that subjet's neutral component. So a lot of these algorithms, with the exception of SoftKiller, use the sort of charged leading vertex, the charged Pileup information, and that's what the sort of organization we're going to try and go after. So jet images we've heard a lot about. You just sort of unroll your detector, and in this case, the jets become an image. Sort of one modification that we've heard about in this track and elsewhere is instead of just having the energy, you can have multi-channel images, where you can have sort of different local information layered on top of each other. So, for example, you can have local multiplicities, or you can separate based on charge to neutral, which is an approach we're going to take. Just a quick overview of things that jet images have been used for. Classification, we've heard about generation with the GANs yesterday, and regression in the sense of predicting a jet image. As far as I know, this is the first work where that happens. And the point of taking an image and cleaning it up or doing something to it seems like it could have applications beyond just Pileup subtraction. So how are we going to organize the information? Well, we know for the charged particles whether or not they come from our interesting vertex. So we're going to have a 3-channel image. One of them is going to be the charged particles of interest. One is going to be the charged Pileup particles. And one is going to be the neutral energy, which you don't know. And with that as your input, you're going to try and predict the neutral leading vertex jet image. This is sort of our regression problem. So the process we used for this sort of case study, we focused on jets, though I'll discuss how you can sort of generalize this algorithm to the event level. What we did is we considered a 500 GeV scalar decaying to dijets, and for Pileup, we layered on soft QCD events, distributed Poissonianly around 140, just as our Pileup distribution. So for the jet image, itself, we use different pixelizations for the charged and neutral information. And most algorithms, for example, convolutional nets, are expecting you to have the same discretization for all the channels. So to get around that, we just did a factor of 4 upsampling of the neutral pixels to the charged pixels to go from 0.1 to 0.025. And just some other information about our jet images. So this is what you're left with. These are your average jet images for the red, green, and blue channels. And the idea is you're trying to take the red, green, and blue and to predict the bottom right channel here, which is the leading vertex transverse momentum. So then there's the question of what architecture do you use. A lot of people sort of assumed, or not at least had sort of the typical slide explaining what the different layers mean. I'll just sort of go over each with one sentence. For a dense unit, you connect your, for a dense layer, you connect every unit to the entire input. For locally connected layers, like these in the GAMs, you connect each unit to a patch of your input with different weights for each patch. And in convolutional layers, it's the same thing, but you share weights for the different patches. So you learn sort of the same function for each patch, which is an interesting feature that you can sort of build into your algorithm. So the architecture we settled on was pretty simple. It was just 2 convolutional layers, 6 by 6 filters, 10 filters per layer. That leaves you with under 5,000 parameters, which is pretty small as far as sort of deep learning architectures go. I wouldn't even call it a sort of deep architecture by any stretch. A feature it does have is that it's local, meaning that the subtraction of a particular neutral pixel, much like in Puppy, depends on the charged and neutral information, sort of a cone around it in the input space. So you can essentially take your trained model and apply it to other locations in your event, just using the surrounding information. So this is sort of just a summary of the framework that we built. So you take your event, in this case a jet, filter it into these 3 categories: the leading vertex charged, Pileup charged, and total neutral inputs. And you run it through your network, which learns how to take that input and tell you the leading vertex neutral information. So with that, the last element to be able to do the regression is to say what you mean by predicting the output. And for that, you need a loss function. So the question is, do you penalize every PT of error the same? Do you want to penalize errors on soft pixels more or hard pixels more? And we found that it doesn't really depend that strongly. But to address the question, we basically parameterize the loss function, where you can go from favoring soft pixels extremely, favoring soft pixels very intensely, to favoring all sort of PT being equal. So, you know, a PT error of 1 MeV is the same on a hard pixel or a soft pixel. And we ended up sort of somewhere in between, sort of a 10 GeV scale factor. Well, I don't want to use it, a scale of 10 GeV in this loss function. And up top, you see an example event without Pileup, with Pileup overlaid, and with sort of 3 of the algorithms. Pummel is the machine learning approach. And you can see that they all do well and sort of predict the events as you expect, with sort of Pummel doing slightly better than our implementations of the other 2. I'll just sort of briefly go through some of the observables we explored, not just sort of at the, are you predicting all of the energy right, but, you know, you sort of project into interesting dimensions of jet observables, how well are you doing? So on the left is the overall distribution of the dijet mass and the jet PT, and on the right is sort of on the per event level, how close the predictions are. So spikier is better on the right, and you can see that we're doing relatively well compared to our competition. Some other observables, mass. We also tried some energy correlation functions, and sort of they all tell the same story, that we're doing rather well on reconstructing the observables. So you can ask the question, how robust is your model? If you train on one type of NPU and test on another, or train on one type of jet process produced by some scalar and test on another, how sensitive is your algorithm? And you can see on the left, training on 20 Pileup vertices, samples with 20 Pileup vertices, you get the low Pileup region well, but you also do better than the competition on sort of the entire space that we explored. And similarly, if you train on in the high Pileup region, you still do rather well all the way down into the low Pileup region. So I just want to take a moment to discuss the question of sort of what is the algorithm learning. And you can usually, see these sort of large arrays of 20 filters that are pretty nice images in sort of the appendix of a lot of papers. But I tried to get sort of a more quantitative feel. So what you can do is you can take sort of the smallest possible tunnel network that sort of just focuses on a single neutral pixel and surrounding charge pixels. And you can sort of ask what it's doing. And here we can see sort of turned off the charged LV information. It's multiplying the charged Pileup information by around -0.5, and it's multiplying the neutral total information by around 1. So we have this sort of function that the thing has learned. And if you sort of look at what linear cleansing does at the jet level, but sort of apply it to calorimeter towers, you get this sort of function. You can see that what the algorithm has learned in this sort of simplified regime is exactly to do linear cleansing of the calorimeter towers with a parameter gamma naught about 2/3, which you sort of expect, they say you expect based on some sort of isospin argumentation. So you can see that even in this sort of very restricted regime, it's learning sort of a physically sensible function. And at least this is how I think about the parameter space. With low layers, low number of filters, you have linear cleansing. You get Gaussian cleansing and nonlinear cleansing as you sort of increase the filter complexity. And as you increase the number of layers, you sort of increase the causal cone of each neutral pixel. So you can sort of encapsulate puppy. And this regime in the middle is sort of the parameter space we explored in our algorithm. I'll just sort of remark briefly that you can learn from data without as many problems as a lot of other machine learning approaches. The sort of data overlay techniques that we've heard about during some of the plenary talks are interesting in that it's sort of creating Pileup data sets the same way we did, where you just sort of overlay Pileup events. So there are interesting ways using minimum bias and zero bias events to sort of get a data-driven training protocol. And I'll just sort of conclude by saying that we sort of have an ML framework with multi-channel jet images, which you could extend to event images, as we heard yesterday in this track, where you use multi-channel for the different information you have. And you can use tools for machine learning, in this case convolutional layers, without going deep, without having millions of parameters, and sort of still spanning a physically sensible space, at least in the regimes we've been able to explore. And I hope I've convinced you that Pileup mitigation can be sort of a good proving ground for using machine learning techniques in high energy physics for regressing and predicting events themselves in the form of jet images. Thanks. So with high Pileup, they become less sparse. Around, I believe we can look here. Neutral N95 is just sort of an infrared and collinear safe measure of how activated your image is. And with Pileup, you get around 40 out of 81, so about half of the pixels are activated in some transmission line.
The sort of network parameters you talked about at slide 13, those come out of an optimization?
So yes, because we have two primary axes, if you're okay with just sort of, let's say, or I guess 3 if you want, filter size, number of filters, and number of layers, and where the number of layers is sort of 1, 2, or 3. We did a reasonable grid search over this sort of space. So beyond this, not so much, but within this sort of, the numbers here, we did a search over.
Any questions? Speaker again.